In this lesson, you will learn how to configure Network Address Translation, NAT, and use it to implement Source NAT and Destination NAT for the traffic passing through FortiGate. In this lesson, you will explore the following topics: Introduction to NAT, Firewall Policy NAT, Central NAT, Session Helpers, Sessions, Best Practices and Troubleshooting. After completing this section, you should be able to understand NAT and Port Address Translation, PAT, understand the different configuration modes available for NAT. By understanding how NAT and PAT work and the available NAT configuration modes, you will have a good start for planning the implementation of NAT in your network. NAT is the process that enables a single device, such as a firewall or router, to act as an agent between the Internet or public network and a local or private network. NAT is usually implemented for one or a combination of the following reasons: improved security. The addresses behind the NAT device are virtually hidden. Amplification of addresses. Hundreds of computers can use as few as one public IP address. Internal address stability. The addresses can stay the same even if Internet Service Providers, ISPs, change. NAT and PAT, also known as NAT, translate internal, typically private, IP addresses to external, typically public, or Internet IP addresses. In FortiOS, NAT and traffic forwarding apply to the same firewall policy. However, diagnostics clearly show NAT and forwarding as separate actions. For outgoing connections, the NAT option in a firewall policy, IP pool, and central SNAT table can be used and known as Source NAT. For incoming connections, virtual IPs, VIPs, and DNAT can be used and known as Destination NAT. NAT64 and NAT46 are the terms used to refer to the mechanism that allows IPv6 addressed hosts to communicate with IPv4 addressed hosts and the reverse. Without this mechanism, an IPv6 node on a network, such as corporate LAN, would not be able to communicate with a website that was in an IPv4 only environment, and IPv4 environments would not be able to connect to IPv6 networks. NAT66 is NAT between two IPv6 networks. When you use firewall policy NAT mode, you must configure SNAT and DNAT for each firewall policy. Central NAT configurations are done per virtual domain, which means SNAT and DNAT configurations automatically apply to multiple firewall policies. This is according to the SNAT and DNAT rules that you specify, as opposed to each firewall policy in firewall policy NAT. As a best practice, when you use central NAT, you should configure specific SNAT and DNAT rules so that they match only the desired firewall policies in your configuration. Both firewall policy NAT and central NAT produce the same results. However, some deployment scenarios are best suited to firewall policy NAT and some are best suited to central NAT. Firewall policy NAT is suggested for deployments that include relatively few NAT IP addresses and where each NAT IP address would have separate policies and security profiles. Central NAT is suggested for more complex scenarios where multiple NAT IP addresses have identical policies and security profiles, or in Next Generation Firewall NGFW policy mode, where the appropriate policy may not be determined at the first packet. Good job! You have been introduced to NAT. Next, you'll learn about firewall policy NAT. After completing this section, you should be able to configure a firewall policy to perform SNAT and DNAT, apply SNAT with IP tools, configure DNAT with VIPs or a virtual server. By demonstrating competence in these areas, you will be able to configure firewall policies to perform SNAT and DNAT, and understand how it is applied to the traffic traversing through FortiGate. There are two ways to configure firewall policy source NAT. Use the outgoing interface address. Use the dynamic IP pool. The source NAT option uses the egress interface address when NAT is enabled on the firewall policy. This is many-to-one NAT. In other words, PAT is used, and connections are tracked using the original source address and source port combinations as well as the allocated source port. This is the same behavior as the overload IP pool type, which you will learn about later. Optionally, you may select a fixed port, in which case the source port translation is disabled. With a fixed port, if two or more connections require the same source port for a single IP address, only one connection can establish. In the example shown on this slide, a firewall policy from internal to WAN 1, IP address 203.0.113.10 is created, and the user initiates traffic from source 10.10.10.10:1025, destined for 192.168.10.10:80. Because NAT is enabled on the firewall policy, the source IP address is translated to the egress interface IP with port translation. IP pools are a mechanism that allows sessions leaving the FortiGate firewall to use NAT. An IP pool defines a single IP address or a range of IP addresses to be used as the source address for the duration of the session. These assigned addresses will be used instead of the IP address assigned to that FortiGate interface. IP pools are usually configured in the same range as the interface IP address. When you configure the IP pools that will be used for NAT, there is a limitation that you must take into account. If the IP addresses in the IP pool are different from the IP addresses that are assigned to the interfaces, communications based on those IP addresses may fail if the routing is not properly configured. For example, if the IP address assigned to an interface is 172.16.100.1/24, you cannot choose 10.10.10.1 to 10.10.10.50 for the IP pool unless appropriate routing is configured. There are four types of IP pools that can be configured on the FortiGate firewall: overload, one-to-one, fixed port range, port block allocation. If you use an IP pool, the source address is translated to an address from that pool, rather than the egress interface address. The larger the number of addresses in the pool, the greater the number of connections that can be supported. For example, in an enterprise network where you require a greater number of connections, or in a network where you want one subnet to use one specific public IP over another to restrict access based on source IP address, the default IP pool type is overload. In the overload IP pool type, a many-to-one or many-to-few relationship and port translation is used. In this example, source IP 10.10.10.10 will be translated to an IP address from the IP pool 203.0.113.2 to 203.0.113.5. In the one-to-one pool type, an internal IP address is mapped with an external address on a first-come, first-served basis. There's a single mapping of an internal address to an external address. Mappings are not fixed, and if there are no more addresses available, a connection will be refused. Also, in one-to-one, PAT is not required. In the example on this slide, you can see the same source port is shown for both the ingress and egress address. The fixed port range IP pool type associates internal IP address ranges and external IP address ranges and disables PAT. It allows fixed mapping of the internal start IP or internal end IP range to the external start IP or external end IP range. The example on this slide shows a fixed port IP pool. The internal address range 10.0.1.10 to 10.0.1.11 maps to the external address range 10.200.1.7 to 10.200.1.8. The two CLI outputs shown on this slide illustrate the behavior difference between the port block allocation IP pool type and the default overload IP pool type. Using hping, a rogue client generates many send packets per second. In the first example, the port block allocation type limits the client to 64 connections for that IP pool. Other users will not be impacted by the rogue client. In the second example, the overload type imposes no limits, and the rogue client uses many more connections in the session table. Other users will be impacted. VIPs are DNAT objects. For sessions matching a VIP, the destination address is translated. Usually, a public internet address is translated to a server's private network address. VIPs are selected in the firewall policy's destination field. The default VIP type is static NAT. This is a one-to-one mapping, which applies for incoming and outgoing connections. That is, an outgoing policy with NAT enabled would use the VIP address instead of the egress interface address. However, this behavior can be overridden using an IP pool. The static NAT VIP can be restricted to forward only certain ports. For example, connections to the external IP on port 8080 map to the internal IP on port 80. On the CLI, you can select the NAT type as load-balance and server-load-balance. Plain load balancing distributes connections from an external IP address to multiple internal addresses. Server load balancing builds on that mechanism, using a virtual server and real servers, and provides session persistence and server availability check mechanisms. VIPs should be routable to the external-facing ingress interface. FortiOS responds to ARP requests for VIP and IP pool objects. ARP responses are configurable. In this example, source IP address 192.168.10.10 is trying to access destination IP address 203.0.113.22 over port TCP/80. Connections to the VIP 203.0.113.22 are NATed to the internal host 10.10.10.10. Because this is static NAT, all NATed outgoing connections from 10.10.10.10 will use the VIP address in the packet's destination field, not the egress interface's address. In FortiOS, VIPs and firewall address objects are completely different. They are stored separately with no overlap. By default, firewall address objects do not match VIPs. In the example shown on this slide, the all address object as a destination in the first policy does not include any VIPs. So traffic destined to the web server VIP will skip the first policy and match the second allow_access. In order for the first policy to match the VIP, you either need to edit the policy on the CLI and set match-VIP enable, which allows address objects to match the VIP address, or change the destination address of the first policy to be the VIP in question. Traffic is permitted to fall through to the next policy. However, when you use VIP firewall policies, there can be some exceptions. When VIPs are configured for incoming WAN-to-LAN connections, it will be first matched against the VIP table. In the example shown on this slide, a firewall policy from WAN to LAN is configured with a specific source and the action is deny. There is a second firewall policy that is allowing access to the VIP, the destination address. Even though the deny firewall policy is at the top of the list, the denied source is still allowed by the second firewall policy to access the VIP. In order to block traffic from the denied source, you must enable set match-VIP enable in the deny firewall policy, which skips the VIP ID checking. Alternatively, you can configure the destination address as the virtual IP in the deny policy instead of all. Good job! You now understand Firewall Policy NAT. Next, you'll learn about Central NAT. After completing this section, you should know how to configure Central NAT. By demonstrating competence in configuring Central NAT to perform SNAT and DNAT, you will be able to use NAT on a more granular level to control IP addresses, protocol, and port translation. By default, Central NAT is disabled and can only be enabled on the CLI. After Central NAT is enabled, these two options are available to be configured on the GUI: Central SNAT, DNAT, and virtual IPs. What happens if you try to enable Central NAT, but there are still IP pool or VIPs configured in firewall policies? The CLI will not allow this and will present a message referencing the firewall policy ID with the VIP or IP pool. You must remove VIP or IP pool references from existing firewall policies in order to enable Central NAT. Central SNAT is mandatory for the new NGFW mode in policy-based. This means SNAT behaves only according to the NAT settings under Policy and Objects, Central SNAT settings. You can have more granular control based on source and destination interfaces in the Central SNAT policy over traffic passing through firewall policies. You can now define matching criteria in the Central SNAT policy based on source interface, destination interface, source address, destination address, protocol, source port. Starting in FortiOS version 6.0, a matching Central SNAT policy is mandatory for all firewall policies. If there is no matching SNAT policy, traffic will be dropped. If the Central SNAT policy criteria matches the traffic based on multiple firewall policies, the Central SNAT policy will be applied to those firewall policies. Similar to firewall policies, a Central SNAT policy is processed from top to bottom, and if a match is found, source address and source port are translated based on that Central SNAT policy. In the example shown on this slide, the Central SNAT policy translates the source IP address to the defined IP pool address 203.0.113.5. However, the translation takes place only if the traffic matches all the variables defined in the Central SNAT policy. That is, traffic from the source IP address through the source interface internal to FortiGate must be destined for destination IP address 192.168.10.10 through destination interface WAN 1, and the protocol must be TCP. For illustration purposes, only a single IP address is used for the destination, and the IP pool type is set to overload with a single IP address. The firewall policy is created from internal to WAN 1. There is no NAT option available in FortiOS version 6.0 firewall policy, and matching SNAT policy is mandatory to pass the traffic. If there is no matching Central SNAT policy, traffic will be dropped. If the user tries any TCP-based sessions, for example HTTP, HTTPS, to the destination IP address 192.168.10.10, the source IP address will be translated to an IP pool address or addresses defined in the Central NAT policy. What if the user tries to send any ICMP or UDP-based traffic to 192.168.10.10? Will the source address be translated to the IP pool defined in the Central NAT policy? As the Central SNAT policy does not match, FortiGate will automatically drop the traffic. What if the user tries TCP-based traffic to another destination IP address, 192.168.10.20? Will the source address be translated to the IP pool defined in the Central SNAT policy? Again, the destination IP address of 192.168.10.20 does not match the Central NAT policy, so FortiGate will drop the traffic. Traditionally, on FortiGate, VIPs are selected in the firewall policy as the destination address. On FortiGate, you can configure DNAT and VIPs for DNAT. As soon as a VIP is configured, FortiGate automatically creates a rule in the kernel to allow DNAT to occur. No additional configuration is required. Do you lose the granularity of being able to define a firewall policy for a specific VIP and services? No, you don't. If you have several WAN to internal policies and multiple VIPs, and you want to allow specific services for specific VIPs, you can define each firewall policy with the destination address of the mapped IP of the VIP, and select the appropriate services to allow or deny. Note that if both Central SNAT and Central DNAT VIP are configured, the outgoing internal to WAN traffic will source NAT to the DNAT or VIP address based on the Central SNAT and DNAT VIP configurations. In the example shown on this slide, a DNAT and VIP rule is created to map external IP address 203.0.113.22 to internal IP address 10.10.10.10. Remember, as soon as a VIP is created, a rule is created in the kernel to allow DNAT to occur. The firewall policy from WAN 1 to internal is created with the destination address all or mapped IP address / range 10.10.10.10 of the VIP. The source IP address 192.168.10.10 is trying to access the destination IP address 203.0.113.22 over port TCP/80. Connections to the VIP 203.0.113.22 are NATed to the internal host 10.10.10.10 without any additional configuration. Central NAT can be disabled on the CLI by running set central-net disable under the config system setting. What happens to firewall policies that are using Central SNAT and DNAT rules if Central NAT is disabled? For new firewall sessions, the incoming to outgoing firewall policies may still work using the egress interface IP address. However, the incoming to outgoing firewall policies will not use the IP pool addresses, which were previously tied to the Central SNAT policy. If you need to use the IP pool, you need to edit the firewall policy to use the IP pool. Egress to ingress firewall policies that use DNAT and VIP will stop working because in Central NAT, the destination address in the firewall policy is simply an address object, not an actual VIP. Without the Central NAT hook into the DNAT table, the address object will cause a forward policy check failure. The traffic will be denied by policy ID 0. You need to edit the egress to ingress firewall policy and select VIP as the destination address. Good job! You now understand Central NAT. Next, you'll learn about session helpers. After completing this section, you should be able to understand how session helpers work, use a session helper for VoIP. By demonstrating competence in understanding how session helpers work, you will be able to use session helpers to analyze data in the packets of some protocols and allow those protocols to pass traffic through FortiGate. Some application layer protocols are not fully independent of the lower layers, such as the network or transport layers. The addresses may be repeated in the application layer, for example. If the session helper detects a pattern like this, it may change the application headers or create the required secondary connections. A good example of this is an application that has both a control channel and a data or media channel, such as FTP. Firewalls will typically allow the control channel and rely on the session helpers to handle the dynamic data or media transmission connections. When more advanced application tracking and control is required, an application layer gateway, ALG, can be used. The VoIP profile is an example of an ALG. In the example shown on this slide, the media recipient address in the SIP SDP payload is modified to reflect the translated IP address. Notice how, because firewall policies are stateful, a pinhole is opened to allow reply traffic, even though you have not explicitly created a firewall policy to allow incoming traffic. This concept is used with some other protocols, such as NAT for IPsec. Good job! You now understand session helpers. Next, you'll learn about sessions. After completing this section, you should be able to understand the session table on FortiGate, understand the session TTL, analyze session diagnose command output, understand TCP, UDP, and ICMP states on FortiGate. By demonstrating competence and understanding how a session table keeps track of the session information, you will be better able to use that information to understand the actions applied to traffic, such as SNAT, DNAT, and routing. You can view the All Sessions page on the GUI, but the CLI provides more information regarding sessions in the session table. Firewall performance of connections for each session and the maximum number of connections are indicated by the session table. However, if your FortiGate contains FortiASIC NP chips designed to accelerate processing without loading the CPU, the session table information may not be completely accurate, because the session table reflects what is known to and processed by the CPU. Each session on FortiGate can idle for a finite time, which is defined by time to live, TTL. When the FortiGate detects the session is idle after some time of inactivity, and TTL is reached, the session is deleted from the session table. Because the session table has a finite amount of RAM that it can use on FortiGate, adjusting the session TTL can improve performance. There are global default timers, session state timers, and timers configurable in firewall objects. The Diagnose Sys Session command tree provides options to filter, clear, or show the list of sessions. You can also list brief information about sessions by running the git system session list command. Before looking at the session table, first build a filter. To look at our test connection, you can filter on DST 10.200.1.254 and dport 80. In the example shown on this slide, you can see the session TTL, which reflects how long FortiGate can go without receiving any packets for this session, until it will remove the session from its table. Here you can see the routing and NAT actions that apply to the traffic. The firewall policy ID is also tracked. The proto_state for TCP is taken from its state machine, which you'll learn about in this lesson. Earlier in this lesson, you learned that the session table contains a number that indicates the connection's current TCP state. These are the states of the TCP state machine. They are single-digit values, but proto_state is always shown as 2 digits. This is because FortiGate is a stateful firewall and keeps track of the original direction, client-side state, and the reply direction, server-side state. If there are too many connections in the SYN state for long periods of time, this indicates a SYN flood, which you can mitigate with DOS policies. This table and flow graph correlate the second-digit value with the different TCP session states. For example, when the FortiGate receives the SYN packet, the second digit is 2. It goes to 3 once the SYN ACK is received. After the three-way handshake, the state value changes to 1. When a session is closed by both sides, FortiGate keeps it in the session table for a few seconds more to allow any out-of-order packets that could arrive after the FIN ACK packet. This is the state value 5. Although UDP is a message-oriented stateless protocol, it doesn't inherently require confirmed bidirectional connections like TCP, so there is no connection state. However, FortiGate's session table does use the proto_state equal field to track the unidirectional UDP as state 0 and the bidirectional UDP as state 1. When FortiGate receives the first packet, it creates the entry and sets the state to 0. If the destination replies, FortiGate updates the state flag to 1 for the remainder of the conversation. Notably, ICMP such as ping and traceroute have no protocol state and will always show proto_state equal 00. Good job! You now understand sessions. Next, you'll learn about best practices and troubleshooting NAT. After completing this section, you should be able to identify common NAT issues by reviewing traffic logs, monitor NAT sessions using diagnose commands, use VIP filters for central NAT, use NAT implementation best practices. By demonstrating competence in using traffic logs, diagnose commands, VIP filters, and best practices for NAT implementation, you should be able to monitor for and troubleshoot common NAT issues and successfully implement NAT in your network. NAT port exhaustion occurs when there is so much traffic traversing the border and being translated that all ports are being used. When NAT port exhaustion occurs, FortiGate informs the administrator by displaying the log shown on this slide with a severity of critical. To address NAT port exhaustion, you need to take one of the following actions. Create an IP pool that has more than one external IP tied to it, so it load balances across them. Reduce the traffic traversing the border. To receive important logs like this one, you must make sure that the necessary logging is enabled. On the FortiGate GUI, click Log and Report, Log Settings, to check that the default setting, logging to disk or memory, is activated. NAT port exhaustion is also highlighted by a rise in the clash counter from the Diagnose System Session Stat command. You can use Diagnose Firewall IP Pool-all list command, which will list all of the configured NAT IP pools with their NAT IP range and type. The Diagnose Firewall IP Pool-all stats shows the stats for all of the IP pools. The stats command provide the following data and information: NAT sessions per IP pool, total TCP sessions per IP pool, total UDP sessions per IP pool, total others, non-TCP and non-UDP sessions per IP pool. Optionally, you can filter the output for specific IP pool by using the name of IP pool. The Services option has been added to VIP objects. When services and port forward are configured, only a single mapped port can be configured. However, multiple external ports can be mapped to that single internal port. This configuration was made possible to allow for complex scenarios where multiple sources of traffic are using multiple services to connect to a single computer, while requiring a combination of source and destination NAT and not requiring numerous VIPs to be bundled into VIP groups. VIPs with different services are considered non-overlapping. Use the following best practices when implementing NAT. Avoid the misconfiguration of an IP pool range. Double-check the start and end IPs of each pool. Ensure that the IP pool does not overlap with addresses assigned to FortiGate interfaces or to any host on directly connected networks. If you have internal and external users accessing the same servers, use split DNS to offer an internal IP to internal users so that they don't have to use the external-facing VIP. Don't configure NAT rule for inbound traffic unless it is required by an application. If, for example, there's a matching NAT rule for inbound SMTP traffic, the SMTP server might act as an open relay. Congratulations, you have completed this lesson. Now you will review the objectives that you covered in this lesson. This lesson covered the following objectives: understand NAT and PAT, understand the different configuration modes for NAT, configure a firewall policy to perform SNAT and DNAT VIPs, configure central NAT, understand session helpers and use a SIP session helper for VoIP, understand and interpret the session table, analyze session diagnose command output, understand TCP, UDP, and ICMP states, use traffic logs to identify common NAT issues, and monitor NAT sessions using session diagnose commands. Use NAT implementation best practices.